Chemistry, Chapter 30, Theory Video 4. We are going to look at nuclear magnetic resonance NMR spectroscopy. Here, what we use is we try to find out how many H plus ions, that is, how many protons are H plus ion is the proton. Because it eliminates the electron, and thereby only a proton would be remaining in the H plus ion. So we find out the how many electrons, how many protons are there surrounding a molecule or surrounding a certain part of the molecule. So this is actually a way that we can identify organic molecules. So here what happens is each hydrogen atom of an organic molecule will behave like a magnet, because these single protons that are there can spin. This spinning motion generates this spinning positive charge generates a small magnetic field around it. So when a chemical is placed in a magnetic field, in another magnetic field, these H plus ions will either arranged in line with it by when it spins in one direction, or arranged against that by lining up in the opposite direction, or spinning in the opposite direction. So this process generates a tiny difference in energy that is between the oppositely spinning H plus nuclei, that is the proton. This energy is going to correspond to the energy carried by waves in radio electromagnetic radiation spectrum in the radio wave region. So that if we can identify, we will be able to figure out what type of or how many hydrogen atoms are present in a place. In NMR spectroscopy, we say that the nuclei flip between these energy levels by gaining that energy. Another important thing that we need to understand is the atoms whose mass number is an odd number. For example, hydrogen 1 or carbon 13 would absorb energy in the range of frequencies that is going to be analyzed. So this gap between the nuclear energy levels will vary depending on the other atoms in the molecule or the molecular environment. So as a result, we will be able to find out where these H plus atoms are there in different parts of a molecule. So if we now look at an example, it will be easy for us to understand. Now CH3OH, as you can see, CH3OH would have different molecular environments for hydrogen. As you can see here, here it is hydrogen 3, then this is OH is going to be like this, right? So in this presence, now this has a different region. This is different to these hydrogens. That is what you need to understand. I hope that makes sense to you. So then when these molecular environments are different, we can identify NMR using the H plus region, using the NMR spectroscopy. We can identify how these hydrogen atoms are there and how they are connected. Now it is easy for us to vary the magnetic field because it is easier than varying the wavelength of radio waves that are going to be absorbed. When the magnetic field is varied, the H plus nuclei that are in different molecular environments will flip at different field strengths, and they will be measured relative to different compounds which starts at a value 0. And this standard value 0 is given to TMS, which is called tetramethyl silane. Tetramethyl silane. So that is taken as the standard value, just like carbon that we take C12 to be 1. Carbon C12 to be 12, we take this as a unit. TMS is given 0. TMS is an inert volatile liquid that will mix well with organic compounds. So it is quite useful for us because it can actually used as a basis on which everything else is described. So now when you take its formula, it is SiCH3 4. So that means all of its hydrogen atoms are equivalent. That is, they are in the same molecular environment, because carbon has for each silicon, for one silicon atom, there are 4 CH3s joined, and for each carbon there are 3 hydrogens joined. So they have the same molecular environment. So because of this, TMS will give only a one single sharp absorption called a peak. Then for most, when in comparison to all other protons, this is going to be at a higher frequency. Then based on a shift away from this sharp TMS on the spectrum, we call which is known as a chemical shift, sigma, and we measure it parts per million, and this shift is what we compare with the standard values. So this is a single peak of TMS which is used as a standard. Then there are the different kinds of NMRs that we learn about, low and high resolution NMRs. But before that, let's write down a note about this. If you have any doubts, please ask. Write down. Nuclear magnetic resonance NMR spectroscopy is widely used to identify organic compounds. This is done by arranging the H plus ions it contains in a magnetic field within brackets, right? Because H plus ions or protons can spin and act as magnets themselves. These spinning protons have different energies because they will either spin in the same direction or the opposite direction. This energy difference will correspond to the energy carried by the radio wave range of electromagnetic radiation spectrum. Please draw this 30.15 graph. So then you will be able to understand how they spin with and against, and that energy difference is easily seen. By looking at this energy level variation, we can identify H plus atom environment, thereby being able to identify the chemical itself. Different field strengths are measured relative to a reference compound, which is given a value of 0. The standard compound is tetramethylsilane, capital T, capital M, capital S, TMS. Within brackets, right? SiCH3 4. SiCH3 CH3 methyl tetramethyl CH3 4. Because it has H atoms having the same molecular environment, it would have only one sharp absorption peak and has a higher frequency than most other protons. Please draw this as well, 30.16. After you are done with it, please do question number 4. In the next video, we will discuss the low resolution NMR and the rest. If you have any doubts, please ask.